Welcome back, everybody. Last time we thought about how we could get parameterizations for a surface. We thought about doing this by describing our surface in a chosen set of coordinates and then using that description to find the x, y, and z for our parameterization. Well, today we come to the payoff of this work where we're going to think about how we can add up information over something two-dimensional, so a surface. And so here the idea is we have some surface hanging out in 3 space, just magically suspended in place. And over each point of that surface, we have some information. So for example, perhaps at this point, that x, y, z, we have some information which we can think of as a function value, right? And if we want, we can take that function value, maybe it's 5, and stand up a stick of that height, right? Of height f of x, y, z. And if we go through and stand up all these different sticks over our surface, what we get is kind of this like mohawk thing, right? This head of hair standing atop our surface. And what we'd like to do is take this picture and our surface and lay it out flat so that these sticks are all now shooting up perfectly vertically. And we want to compute the net volume of what we have. And what does that for us is a surface integral. So we use 2 integral symbols since what we are integrating is two-dimensional. And here, this is a big S behind the D, and we're adding up our function information over our surface. And this is what is going to go through and add up all this information and hand us the net volume that we have. So geometrically, this is what's going on. How do we algebraically compute such a thing? Well, what's nice is that we have the exact same 2-step process as we have for line integrals. Right, step 1 is still the same. We need to get our hands on some vector function that will go through and hand us every single point, on our surface. Right, we need to parameterize our surface. And once we have that parameterization, we can go ahead and translate our integral. And so here in the box, this is our translation formula. So we translate to a double integral over our parameterization domain of our function, where we sub in into x, y, and z in terms of what they are from our parameterization. And we have this thing over here that's showing up. And what's great, what I'm really excited to share with you is that they're just like with line integrals, there's a catchy mnemonic for remembering what comes up in our translation formula. Are you ready? It's multiply by the size of the cross product of the partial derivatives of our parameterization. It's so catchy, right? You don't even need to try and memorize it. You've already memorized it. It's so catchy. Oh, there's not really I don't know. I don't know anything that's better than that. This is what shows up. The size of the cross product of the partial derivatives of our parameterization. So I want to talk a little bit about why this shows up, what part this is playing in our formula. So let's slide on down here. First of all, I mentioned this just a second ago. So f of r, this is just shorthand notation, means sub in everything from our parameterization. right? And our parameterization, since we're parameterizing a surface, is going to be in terms of two variables, two parameters, which just in general we call u and v. So we'll swap all that in. But what about that size of the cross product bit? Well, what I claim is that what that's doing is it is representing a little chunk of area. This here in our formula represents the area on our surface from a small change in our parameters u and v. And here's the picture. Right, so here's our surface S, and let's imagine that we kind of pick a special point that we're going to kind of base ourselves at. Now, if we now take this point, which corresponds to a particular choice of u and v, and we just let u vary, so we start cranking u up, that's going to move us along our surface, right? So this is just moving u with v held constant. And similarly, we can take just v and crank that up a little bit, and that'll move us along our surface in a different path. All right, so this is what we get if we just move v, holding u constant. And so here, we see a little patch on our surface, a little chunk of area. And the idea behind our integral is, once again, the motto of calculus. We'd like to approximate this little patch of area and then make that approximation better and better. And the way that we can approximate this little patch of area is actually very similar to how we approximated the patch of area on a graph of a function when we were trying to come up with our formula for surface area. Do you remember how we did that? We used a parallelogram, right? And that's the exact same idea that we're going to use here. So the idea with how to get that parallelogram is that our partial derivative vectors of our parameterization with respect to u is going to give us a tangent vector to this path that we get when we just move u. And similarly, our v is going to give us a tangent vector to the path that we get as we just move v. And so from these two vectors, we have two tangent vectors to our surface. They might be really long, but if we scale them by the small change in u and the small change in v that we got, that'll kind of shrink them up. So the idea here is if we take, say, ru times the small change in u, well, that's going to take this vector and shrink it up a bit. Maybe give us something like this. Both be going in the same direction. Right, just a shrunk version of that. And similarly, if we take rv and scale it by the small change in v that we used, well, then that's going to shrink up this vector and give us a vector more like this. And once we have these two vectors, right, we can look at the parallelogram that they define. And we have a nice formula for that area of a parallelogram, right? Way back in the days of chapter 12, right, the area of this thing is the size of the cross product, right? The size of Ru change in U cross Rv change in V. And the idea is that we can pull out these scalings here, and what we get is Ru cross Rv times change in U, change in V. And the idea is that this thing is approximately equal to the area of that little chunk of s. But in the limit, what's going to happen right, as we shrink up, as delta u, delta v go to 0, this approximately is going to change to an equals, and right, the delta u, delta v, those are going to change to the du, dv that we see in our integral. And so this is what's going on. This perhaps strange seeming part in our integral is just representing a little chunk of area on our surface. And so the kind of geometric interpretation here is that what we're doing on our surface S is we're taking and getting a little chunk of area and then multiplying that by our function, right? And that's just going to take this thing, this little patch of area, and that's going to scale it up by our function and give us a piece of net volume, right? And the integral goes through and adds all this up and hands us the net volume that we want. So that's what the different pieces of this integral are up to. And with that, we have all we need to go ahead and work an example. So let's look back at our ice cream cone that we parametrized last time and make use of the work that we've already done. So here, let's compute the surface integral. Again, this is a big S for the surface integral. Right, when we do the little s, that's if we're doing the line integral. So the surface integral, adding up the information of x squared over our ice cream cone. And so again, to work this out, to compute this surface integral, we have our two-step plan for success. Step 1 is parameterize our surface, and we've already done that, right? For example, we used rectangular coordinates to describe our cone. I just plopped what z equals in terms of x and y into the z component, and we said we could use x and y as our parameters. And the shadow of our cone here was the unit circle, right? Filled in, I guess I should say, unit disk in the xy plane. And so we can just leave this as our description. And in general, this is going to be how we want to parameterize our surfaces. It turns out that it's generally cleanest to use rectangular to get a parameterization, and then use that rectangular parameterization to then translate the integral. And then when the dust settles, only then switch to polar, if we have a nice polar region, and it makes sense. It just turns out that working through the size of the cross product of the partial derivatives gets messy if we switch to polar right now. Much cleaner and rectangular. So anyways, we have our parameterization. Next is we want to use our translation formula, right, with the slick catchphrase, and this is what it becomes, right? Our function doesn't need to be changed at all since x is one of our parameters, right? X is just x, so x squared stays x squared, but then we get this size of the cross product term, right, that's helping represent some chunk of area. So at this point, pause the video, see if you can work out the size of the cross product, and even continue on and fully compute the integral that we're left with. See how far you can get. All right, well, let's talk about this one here. So we kind of have just a few steps to work through. First, the kind of innermost part of this thing, we have these two partial derivatives. So that's step one. Taking the partial derivative of our parameterization, I guess I should bring that up. There's our r hat. So with respect to x, we get 1, 0, and then we have a chain rule here for our square root bit. This is how it works out. And happily those factors of 2 cancel. And a very similar story plays out for the partial with respect to y. Right, once we have those partials, we can then take their cross product. And so here I'm just imagining we have something like this going on, and right, so we do this like we would any other cross product, right? We set up our 3 components and we slap our negative in the middle. And then for our first component, right, we'll forget about I guess the first row up here that we don't see, and the first column, and we do our, in this case, 0 times bottom right minus top right times 1, and so we get minus this stuff. And playing this out for the y and z components, forgetting the middle column and then the right column, doing those derivatives, this is what we end up with. And once we have our lovely cross product, we can go ahead and take its size, right? Just like we would the size of any other vector. So we have our generalized Pythagorean theorem, adding up the squares of our components under the big square root. And so here we get some nice cancellation that happens. All right, so here the square does distribute nicely to the numerator and denominator in both of these. Since squares, exponents do distribute nicely over multiplication and division. And so square goes away in the bottom, and in fact, we are left with lovely common denominators here. And when we combine these two fractions under that common denominator up top, we have x squared plus y squared, which is exactly what we have in the denominator. And so this stuff just becomes a big fat 1. And so at the end of the day, the size of the cross product of our two partial derivatives of our parameterization, which in general is a hideous monstrosity in terms of x and y, here just a nice clean constant root 2. And so that's what gets plopped in for this box here. And with that, the dust has settled in terms of our simplification, and now it's the time to switch over to polar. All right, and so here we were integrating over our unit disk, so that's r from 0 to 1, theta from 0 to 2 pi. X then becomes r cosine theta squared. We have root 2, and the dy dx, that becomes our r dr d theta. And so simplifying a little bit, what do we have? I guess we can pull out the root 2 out front, and then we have 3 factors of r and a cosine squared theta, dr d theta. And at this point, I'll leave it to you to work through our nice clean double integral here. Looks like we might have to use a double angle formula here in our cosine squared to work that out. I do have what you should be able to get to. Just 1 second, it's not right in front of me. Okay, it is the lovely pi root 2 over 4. That fraction got a little bit out of control. All right, so that's the finish line there for that integral. But in any case, that's how it can look to take a surface integral and walk through our 1-2 step process. Right? In general, we'd have to come up with our parameterization, but here we were able to use our work from last time, piggyback off that, and then once we have our parameterization, we can use our translation formula and just take that as a recipe, put in the pieces where they go, and then when the dust settles, if we need to, if it makes sense, we can switch to polar coordinates if we'd like, and then we just have a nice, clean double integral at that point to work through. So some closing notes about this stuff. So here we had our cone, and we were able to parameterize it just by taking the equation for that cone and sticking it in for the z components on our parameterization. And the reason that we were able to do this is because this is really just the graph of a function, right? Of some function of x and y. And we can always do this. If we have a graph, z equals some function of x and y, we can always take that and just plop it in for our z component. We still would need to figure out our parameterization domain, right, our shadow, but we can always get at least our vector function real quick and clean just by plopping that in. Similarly, this works if we have a function not of x and y, but say y is a function of x and z. We can take that function there and plop it in for the y components. Similarly, if that is a typo, that should be if x is some function of y and z, we can plop it in for the x component, and we can quickly get our parameterization function at least. Might need to do a bit of work to find the domain. Last note here. From our work at double integrals, we've seen that if we have some region in the plane and we puff it up by 1, and do a double integral of our constant function 1 over that region, that hands us the area of that region. Well, what we have here is a more general formula, right? Thinking about a general surface integral. If we take that surface and puff it up by 1, geometrically, we're still going to be computing the area of that surface. And again, this is a typo. I'll fix that on your notes. The surface area of our surface, right? If we have some surface S, we puff it up by 1, integrate that, that's going to hand us the area of this thing. And since this surface is floating around in 3 space, we use the language of surface area for what we're computing. So we have a nice general formula for the surface area. But you might recall that back a little ways in this semester, we actually did think about surface area for graphs of functions. And we came up with our formula there. It turns out that if you use the parameterization that we talked about up here for the graph of the function, and you work out this surface integral using our translation formula, we end up with that same formula that we got back in 15.6. And so this matches that formula from before, but this also applies to much more general surfaces that are floating around in 3 space. That's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.